Hello everybody, and welcome to our video on functions of several variables. So we're going to start with just talking about a function f of two variables, which is a rule that assigns to each ordered pair of real numbers xy in a set D a unique real number denoted by f of xy. The set D is called the domain of f, and its range is the set of possible output values. That is, f of xy such that x and y are in D. Looks like we're missing a little bracket there. So let me just, much better. Okay, so where were we? Example 1, find and sketch the domain of f of xy. So a big part of understanding these functions of two variables, which we can think of as three-dimensional functions that create surfaces in 3 dimensions. A big part of what helps us understand them is if we can picture their domains, so we sort of know what region they lie above. So in this case, what do we know? We know that y has to be greater than or equal to 0, since it's in the square root. And we also know that 25 minus x squared minus y squared must also be greater than or equal to 0. So that means x squared plus y squared has to be less than or equal to 25. So if we sketch this, well, what do we see? Well, this here is the circle and the inside of the circle, right? So this is a circle, radius 5 with interior, and we call that disk. But this restriction here tells us that it's only going to be the top half of the circle. So it should look something like this. Okay, so in set notation, what we would say is that x and y is the set of points that satisfy y is greater than or equal to 0, and x squared plus y squared is less than or equal to 25. Okay, so let's talk about graphs of these functions. So the graph of z equal to f of xy is a surface in 3D, and we can visualize the graph of s of f as lying directly above or below its domain in the xy plane. So s is our surface, f is the function that generates that surface, and if we know where the domain is, then we can visualize that that surface is just what's directly over that domain. Okay, so let's go ahead and try to sketch the graph of this function. And actually, this is something we've already seen before. So if we write this in the form z equals 7 plus 4x minus 3y, if I subtract the z, we can put this in one of our standard forms for the plane. All right, so that tells us this is a plane, an equation for a plane, I should say. And what else do we know about this? So this is a plane, and it has normal vector 4, -3, -1. That's just those coefficients. So let's try to sketch this. So I think it's usually sort of easiest, or at least it's often easiest, to get your bearings by plotting a single point and then try to, graph the shape around it. I think it makes it easier to make the picture look right. So in this case, if we had x and y were 0, then z would have to be 7. So that tells us if we plot z equals 7, that this has got to be a point on our graph. Now this normal vector sort of tells us the opposite of the direction, right? This is orthogonal to the plane. So if we draw this, we know the plane is at a right angle to it. Now, I'm not going to be able to draw this quite perfect, but let's just sort of sketch it out. So if I go out a distance of 4 in the direction of the x-axis, and then 3 in the direction of the y-axis, and then I go down 1 in the direction of the z-axis. So this tells me my normal vector should end up being something like this. And so your plane, so you have to imagine this is coming sort of towards the screen and also towards the left and a little bit downward. And so the plane should be orthogonal to that normal vector. And that kind of makes it look like the plane should be something like this. Of course, keep in mind this plane goes on forever, but we can't draw something that's infinitely big, so just, draw a little rectangular region. Okay, so as I've said before, I never expect these pictures to be perfect. Just draw them in such a way that you communicate some information about them, illustrate that you understand what's basically going on with these things. All right, so let's go ahead and sketch the graph here of g of xy equals the square root of 25 minus x squared minus y squared. All right, well, the first thing we know is that since this is a square root, that tells us that everything inside the square root has to be greater than or equal to 0. Well, if we add x squared and y squared to the other side, that tells us that x squared plus y squared has to be less than or equal to 25. So in the case of this particular graph, our domain is actually the circle. So if we just look at the domain, so in 2 dimensions, okay, so we're looking at this domain, but now we want to look at what's happening to the function in 2 dimensions over this domain. Or the function in 3 dimensions over this domain, sorry. So on our xy plane here, we see that we have a circle with radius 5. And maybe I'll just extend my z-axis a little to give it some room to breathe. Now, let's just plot our point when x and y are 0. So that gives us the square root of 25. So that actually plots us right up at 5 here. Well, you might kind of realize immediately what this thing is, but if not, let's take a closer look at the equation. Sometimes we can just determine what the graph looks like from the equation. Sometimes we've got to actually plot some details. So in this case, if we actually went a little bit further with this equation and manipulated it further, we'd have z equals this square root. So z has to be strictly positive here. But if we squared both sides, assuming z was positive, and we added the x squared and y squared to the other side, we get x squared plus y squared plus z squared equals 25. So that tells you this is the sphere with radius 5, but we have that restriction that z is greater than or equal to 0. So what do you see here? This is a semisphere with radius 5 above the xy plane. Okay, so hopefully that made sense. Let's go ahead and move on to another idea here, the idea of level curves or contour curves. So level curves are a really helpful tool in visualizing things. In particular, it's obviously quite hard to draw some three-dimensional surfaces, but level curves are much easier to draw and can still give you an idea of how the behavior of the curve acts in 3 dimensions. So the level curves of a function f of 2 variables are the curves with equations f of xy equals k, where k is a constant. So in other words, what you do is plot on a 2D graph a bunch of curves that show you where a function takes certain values. So if we look at this, this is a nice little public resource. You can actually find level curves for maps all over the United States, and those are totally free resources. So this one is, I believe this is in Tennessee, if I'm not mistaken. So we've got this Stone Mountain here, and you see all these little curves on this map. And it's this is a bit of an old scan, so I'm going to see if we can zoom in a little bit here to see what's written better. But you can see that there's some numbers written on some of these. Like that looks like it says, maybe, here's one you can read, 2,500, right? So this is 2,500. So that's telling you the elevation along this curve. So if you were to trace all along this curve, everywhere on that curve has an elevation of 2,500, which I think this is in feet. I'd have to check. I didn't look at the key. But that's the idea. Each curve represents a height, and usually these curves will be labeled according to that height. And so you can get a sense that, okay, so this looks to be about 3,000. So everything on this curve is 3,000. And you can see that the curves are getting higher and higher. The height values are getting higher and higher as you go in towards this ridge. So even though level curves are drawn in 2 dimensions, they still give you good information and help you kind of visualize what's happening in the 3-dimensional world. Okay, so let's go ahead and move on and draw a contour map of the following function, showing several level curves. So this might seem more complicated than it is, but it's actually a pretty easy idea. So what we're going to do is write this as k equals x cubed minus y. And I'm going to solve this for y equals, so I get y equals x cubed minus k. And so what we're going to do is just draw several graphs of this form where k is a constant value. So we'll just pick some values. How about k is -2, k is -1, k is 0, k is 1, and k is 2. So then what do we get here? We get y equals x cubed plus 2, right? Because those negatives cancel. Y equals x cubed plus 1. Y equals x cubed. Y equals x cubed minus 1. And y equals x cubed minus 2. Okay, so let's start with y equals x cubed. So that's a cubic function. I actually need to go up to 8 here. So we'll label this as k equals 0. Now all of these are just shifts of this graph, but here this is a shift up 1, and it corresponds to k equals -1. So we shift up 1, so the graph looks like this. Shift up 2. All right, sorry, that should be k equals -1. I just said that, and then I wrote the wrong thing. Okay, so k equals -1. Now when we shift up 2, that's going to be k equals -2. I'll mark this one down here. And now we'll look at these two graphs. So for k equals 1, that is a shift down 1. And for k equals 2, we get a shift down 2. So hopefully this kind of helps you picture what's happening in 3 dimensions, right? You've got this curve where the height of this thing is 0 the whole way through the curve. And as you trace out along the shape of this curve, what you get is something that's growing in height the further you go out in each direction. Okay, so let's take a look at this, at functions of 3 or more variables now. So a function of 3 variables is just a rule that assigns each ordered triple xyz in a domain D, which is a subset of R3, a unique real number denoted by f of xyz. So for example 5, what we're going to do here is just sketch the domain of this function of 3 variables. So obviously if we have 3 independent variables, and then we have a 4th output variable, we can't directly draw that, right? That's a 4-dimensional function, you could think of it that way. But we can at least draw the domain and understand what kind of values it's acting on, so let's do that. Now for the natural log, we know this input always has to be strictly greater than 0. So let's write that out. So if this is greater than 0, and I move all of my variables to one side, this gives me 16 is greater than 4x squared plus 4y squared plus z squared. And now you might recognize that this looks sort of like an ellipsoid, well, sort of like an ellipse type equation, and we call this in 3 dimensions something like an ellipsoid. But let's try to put it more in that standard form. So what do we get? We divide everything by, let's say, divide everything by 16. So it looks like the domain here is everything that's inside of whatever this figure is. So what I'm going to do here is just start by plotting a couple simple points. So we'll plot the point when z and y are 0. And what I'm really plotting here, I should say, is not a point per se, it's the boundary of this thing, right? Because this all has to be strictly less than 1. But if z and y are both 0, then the boundary here would be when this is equal to 1. So that would be when x is 2. So everything in green, keep in mind, is just a boundary of this domain. The domain is just what's inside of this thing that we're drawing. Now, if we did the same thing and we fixed x and z as 0, we would get y equals 2. Now we would also get the negative values of x and y here. So our xy plane is going to look like this, basically. So it looks like a circle. In other words, when we fix z equal to 0, this portion of our domain here looks just like a circle with radius 2. Now let's look at what happens when we fix x and y at 0. Along our border, we would get z equals 4. So the figure that we get ends up looking like this. All right, that's a little bit hard to visualize, especially with my terrible drawing. But the thing to understand is this is sort of like if you took an ellipse and you rotated it around the z-axis. So if you had an ellipse on the z and y-axis and then you just rotated and spun that around, that three-dimensional figure you get is what we're talking about here for this domain. All right, so let's go ahead and move on. So now we're going to find the level surfaces of this function that has 3 inputs. So that means each level surface itself is going to be a three-dimensional drawing, and the output is in some fourth dimension that we can't draw directly. So this goes to show you another value of the idea of level surfaces is that you can even apply them in this case where you're talking about things that you definitely would not be able to draw visually in a three-dimensional space, even with some sort of app. Okay, so what we're going to do here is just rewrite this as x squared plus y squared plus z squared equals k. So that means this is a sphere with radius square root of k. So in this case, I'm only going to draw a couple, really 2 particular examples of level surfaces. It's more important that you just understand what these level surfaces are, so then you can kind of predict the behavior of the function using that. So first we'll start with k equal to 1. So if k equals 1, that's just a sphere with radius 1. And so rough drawing of this. Yeah, that's not that bad, actually. K equals 1. Now, if k is equal to 4, then we get a radius of 2 here. So I'll draw this one in green, I guess. All right, so what you can see here is that each of these level surfaces looks like a sphere, and the further out you go from the origin, the larger the values of f of x, y, z become. So your smallest values are going to be at the origin, 0. And as you grow out larger and larger, you get values that are going to be obviously larger as well. Okay. Well, that's it for this section. Thank you everyone for watching. Have a great day.